See, the first thing we must know when we do GOC is about the electronegative series, correct? So the fluorine, oxygen, chlorine, nitrogen, bromine, sulfur, iodine, phosphorus, and then hydrogen. This sequence of elements is very important, okay? Because majority of the properties depends on those electronegative series. Next, you will have various electronic effects, out of which inductive effect is the one. Inductive effect, we have two kinds. One is plus I and minus I. So to be more precise, inductive effect is, shifting of sigma bonds. Sigma bonds, okay, uh, between the nucleus. So between the nucleus, there is a small shifting of nucleus, shifting of electrons, sigma electrons, that causes inductive effect. There could be plus psi effect or minus psi effect. Plus psi is donating species. So you see O minus, anything which has a negative charge will be the strongest donating. Then CO minus, then tertiary, secondary, primary, and methyl with deuteriums, methyl with hydrogen, then tritium, deuterium, and hydrogen. This is the sequence of plus I. Clear, beta? While minus I, you know that plus I groups will be more withdrawing. So Nr3 plus, NH3 plus, these are more withdrawing than NO2. Then cyanide, sulfonic acid, then aldehyde. Remember, this is an exception. Aldehyde will come in between. Aldehyde is more than acid. Then halogens, fluorine, chlorine, bromine, iodine. Then we have esters, amides. Then we have ketones, alcohols, thioalcohols, amines, uh, alkynes, then phenyl and double bond. Okay, so these are minus I cases. Clear, beta? You know that distance always is a dominant factor over inductive effect when it comes over the electronegativity when it comes to inductive effect. And if the plus I character increases, the stability of the anionic species will decrease. If minus I increases, the anionic character will always increase. If you have plus I, the cation will become more stable. If you have minus I, the cation will become less stable. So you can see if there is any electron withdrawing group and CO minus, that is more stable than any HCO minus or electron donating group. Clear? Is it making sense? Right. Check out in this example, bromine is withdrawing group, chlorine is withdrawing group, fluorine is withdrawing group. But distance comes the first factor. That's why bromine is given more priority than chlorine than fluorine. Okay. Next. CF3 and CCl3, if you compare, CF3 is more strongly withdrawing. Therefore, this is more stable than anion here. While carbocation, you know that stability decreases if more withdrawing groups are there. So CF3 is strongly withdrawing, so this is less stable and this is more stable. Similarly, CH3 minus is more stable than ethyl ion, while CH3 plus is more stable compared to CH3 plus. Now, this is about inductive effect cases. Next is mesomeric effect, wherein if you have any group around benzene, if it carries a lone pair, it will always donate electrons to benzene. That is called plus M effect. And it will try to increase the electron density on benzene. While if there are no lone pairs on X, and if it has some double bond character supportive, then the double bond will shift on to X and thus giving minus M effect. Minus M effect will always decrease the electron density on benzene. Okay, bache? Any doubt here? Plus M and minus M? Okay. Check out what are the plus M groups. You may have noticed that all of them have a lone pair on it. So NH2, NHR, NR2, OH, OCH3, NCOR, OCOR, halogens, then NO, SO, SO2H, SOR, and then double bond, and then double bond OH and double bond NH2. Clear? This is plus M, minus M. Minus M are those groups, minus, I mean, NO2, cyanide, SO3H, acid, esters, aldehyde, I mean, ethers, ketones, aldehydes, esters, amides, C double bond O. See, none of them, the directly connected group does not have a lone pair on them. Okay. Now the groups which can show both plus M and minus M, this is something you guys must remember, because on one end they have a lone pair and the other end there is a double bond outward which will pull the electrons from benzene. Okay, so let me show you how. For example, if you have benzene here and it is connected to N double bond O, it has a lone pair, and due to lone pair it can donate the electrons here like this, but at the same time, the double bond can be pushed outward. Okay, like this, double bond can be pushed outward and this will take it as O minus, so that means it is showing plus M also, I mean, sorry, minus M also. NO is showing both plus M and minus M group. Girls, clear on this, beta? What is the important point here? Either the connected carbon, sorry, the connected group to benzene must have a lone pair, or it should be simply a double bond or a triple bond form like this. If it is only a double bond also, it will give you both plus M and minus M effect. Okay. Next, groups which give minus I effect on benzene. Okay, all of these group will give you minus I effect on benzene. NH2, OH, NR2, OCH3, everything. Correct. So I want you to go through them list by list, which of them are giving minus I in this case. Because watching them, you should know that they are giving minus I, but majority of them also giving plus M. Got it? So they are giving minus I also, and at the same time, they are offering plus M also. So just try to focus on that part. Yeah, just a second. Sorry. Right? This clear? These are all the minus I groups. Next, we have plus I groups. Plus I usually have minus charge on them, or else they'll be simple alkyl groups like this. These are all plus I groups. And next, activating groups. See, groups which increases the electron density on benzene, these are called activating groups. And groups which decrease the electron density on benzene, they are called deactivating groups. Now notice NR2, NH2, OH, OCH3, if you compare, their plus M is extremely strong compared to their minus I. Although all of them show minus I, their plus M is very strong. So they are called strongly activating groups. Okay. Likewise, if you have OCH3, NHCOCH3, OC double bond to CH3, these are again showing plus M effect greater than that of their minus I, and they are moderately donating to benzene. They are increasing the electron density. Lastly, weakly activating groups, that includes all the alkane where there is no plus M effect, rather they have hyperconjugation. So you can see these three hydrogens will give you more hyperconjugation than deuterium, then two hydrogens, then single hydrogen. Then there is no hydrogen. Okay, clear? These are activating groups. Deactivating groups are these where you have minus I greater than that of hyperconjugation here. So F, Cl, Br, I, these are all going to give you minus I effect. Next, minus I compared to that of plus M. You see, fluorine, chlorine, bromine, iodine, NO and SO2H. These are very important cases because they actually are withdrawing, but at the same time they are donating by plus M. But this is one of those cases where the minus M minus I is dominant over plus M. Okay. Otherwise, we normally check that plus M is very strong, but here it is minus I greater than plus M. Next one is minus I greater than hyperconjugation. Check out CHF2, CHCl2, CHBr2, CHI2. Okay. In this order, if you notice, minus I is greater than hyperconjugation. Next, minus M being greater than minus I, in which case? See, in these aldehyde, ketone, ester, all of these cases, minus M is greater than that of minus I. Okay. And this is moderately deactivating. Next, I is very, very strong than minus I. That includes NO2, cyanide, SO3H, COOH. And at the same time, NR3 plus, NH3 plus, NHR2, CF3 and CCl3. These are all only with minus I, but they are also very, very strong. Okay, clear beta? So quickly go through that, write and learn, both of you, what are activating and deactivating. Now check when it comes to acidic character, how you need to figure out. Check out. When it comes to left to right, compare the electronegativity difference only. That is, if you take methane to HF, okay, if you take methane to HF, you can see HF will have the highest acid because of its more electronegativity difference. Okay, and the conjugate bases will always be opposite, correct? So CH3 minus will be more basic, then NH2 minus, then OH minus, then F minus. Okay, while when it comes to down the group, here, when it comes to down the group, bond dissociation energy only need to be compared. Got it? So if you have more bond dissociation energy, acidic character will be less. See, down the group, HI requires the least amount of energy. Because it requires least amount of energy, okay, this is more acidic. So you can see acidic character, HI is greater than HBr than HCl. Okay. While removing H plus, you will get, anions which are basic. So F minus is more basic than Cl minus, then Br minus, then I minus. The same logic applies to even group 16 also. H2T is more acidic than H2SE, H2S and H2O. Even if you write in terms of phenolic position also, phenol will be less acidic than, thiophenol, than sinyl phenol. Clear beta? This is how the acidic character will vary, right? This is, I have written one left to right, one down the. Okay. Next. Okay. So check out. If it is alcohols, okay, methanol, methanol, ethanol, and propanol. If you go from left to right, the acidic character will decrease because CH3, CH2 will give you more plus I compared to ethyl compared to methyl. Therefore, this is more acidic. Okay, this is more acidic here. Next, check out. Next, this is propanol. Okay, then we have isobutanol and secondary butanol, and therefore tertiary butyl alcohol. Okay, so all of these again, if you notice, they will be decreasing their acidic character from left to right because of more plus I effect. Done. The minute you remove H plus, now you will have methoxy group, ethoxy group, and propoxy group. All of these are, this is how the basic character varies. And out of all of these, you can see the tert butoxide is the most basic group. Tert butoxide is the highest basic group because that is the least acidic form in its tert butanol form. Okay. Next is, you can see this is all going to be uh, sp2 carbons, 1 2 3 sp2 carbon with alcohol. These are these are all sp3 carbon. Now we have sp2 carbon, then we have sp carbon. So sp is more withdrawing here, so because of which the acidic character will increase. All right. So that is how the acidic character should be checked. Okay. And next, phenols. Check out in case of phenols. See, phenol, methanol, and water, if you compare. See, methanol and water is a special case, right? Methanol and water is special case. Methanol is slightly greater than water. But in phenol, you know that removing H plus ion, you will get O minus, and O minus is resonance stabilized. And that's the reason phenoxide is going to be more acidic. Okay, next. If you have methoxy group and ortho, meta, and para, methoxy groups and ortho, meta, and para, you will see at ortho position, you will have both hyperconjugation as well as high plus I effect. Meta position, you will never apply hyperconjugation or mesomeric effect. Keep that in mind. And para position, you will have, hyperconjugation as well as plus I effect. So putting all of these three together, you can see the most donating position is ortho. Next most donating position is para. Next is meta. So least is only hydrogen, which is phenol. So phenol, meta, para, and ortho. That will be the order of acidic strength for phenols. If you have OCH3, OCH3 on ortho position will show plus M, para position it will show plus M. And because it is also showing minus M, you can see minus M decreases as the distance increases. Now we can clearly make out that meta is the most withdrawing, correct? And then ortho and para are donating. Within that, ortho is slightly more withdrawing, correct? Because, sorry, ortho will have more minus I. So that's supposed to have more acidic character than para. So therefore, MHOP, that will be the acidic character. While cyanide is strongly withdrawing group. It is withdrawing by minus M, it is withdrawing by minus I. On meta position, you will not apply any minus I effect and minus M effect, but minus I effect is applied on ortho, meta, and para. It decreases from ortho towards para. Putting these effects together, you will see ortho has most withdrawing group, then para, then meta, then hydrogen. So you can notice this is the order. Okay. So fifth one, theoretically it should be ortho, para, meta, and hydrogen. But unfortunately, between H and oxygen, there will be hydrogen bonding in ortho position. That's why para will slightly overpower the ortho position. So this is the actual, acidic condition, acidic character for phenolic groups. Okay. We also quickly go through the effects also. Check out all the examples. Quick. In the case of carboxylic acid, if there is any group G here, like NO2, cyanide, all of these groups, if you compare, only check out on the basis of plus and minus I. You can clearly notice that NO2, cyanide, SO3H, COH, Cl, all of these along with OH and NH2, these are all withdrawing groups. In fact, OCH3 also. So put all the withdrawing groups based on minus I. So you can see minus I order is like this up to NH2. And thereafter, hydrogen will come, then CH3. CH3 is donating. Okay. Clear? Now notice when it comes to benzoic acid, especially in benzoic acid, these are the orbitals you have. The green ones which I have written, these are all the orbitals we have, correct? And in acid, basically this pi bond can move here, the pi bond can move here, this pi bond can move. That's how the resonance is happening. Okay. In fact, after removing H plus also, you will have this resonance as well as this resonance happening. But by chance, if there is any bulky group at ortho position, now this group and this group, they both will repel with each other. Thus, this orbital will not be in the same plane as this orbital. And if they are not in the same plane, the pi bond cannot happen. So if the pi bond cannot happen, the resonance structures of CO minus will be retained. That means there is no donating group. No donating group will always increase the acidic character. Therefore, which offers steric hindrance more the steric hindrance, which you call it as steric inhibition of resonance. If you have more such groups or bulkier the groups, more is the acidic character. So you can see these are all those groups which can offer the SIR effect. Okay, that means if they are present on ortho position, they will be more acidic in nature. If any of these groups are present at ortho position, they will make the benzoic acid stronger acid. Okay, so you can see phenomena where SIR effect is at ortho position increases the acidic character compared to other locations. Clear? Clear? So that is about the ortho position. So phenomena where SIR groups at ortho position, got it, increases the acidic character compared to the other locations. So you can see at ortho position, you will not see any hyperconjugation or hyperconjugation plus psi or anything. You will only check out ortho effect. Correct? If ortho effect is there, means automatically it is most acidic. Then next in at meta position you have only plus psi, and in para position you will have plus psi as well as hyperconjugation. Therefore, ortho, then hydrogen, then meta, then para. So that will be the acidic character. Next, if you have NO2, again at ortho position, you will not notice anything. Simply you check out ortho effect. So that is the most acidic. Then compared to meta and para here, at meta position, you will notice that NO2 minus I is present, and para position you will have minus M minus I both present. Ortho effect is absent. So therefore, ortho, para, meta, and hydrogen. That will be the acidic character. Clear? Right. See, even if you have something like OH, okay, at ortho position, if you have OH, it is not giving any steric hindrance, but it is giving hydrogen bonding after removal of this H plus. You remove the H plus, now you'll get a hydrogen bonding here. Now that hydrogen bonding is highly effective. Okay, so you will notice an intra H bonding happening here. So you can see at ortho position, you will because of this intra H bonding, you will also call that as a ortho effect. So due to ortho effect, it is most acidic, then meta, then hydrogen, then para. Clear? This will be the intra H bonding. Okay. So I guess you understood how to check out the ortho effect on both the cases, beta. Right. Next thing is about basic character. Basic character is mainly observed in alcohols and amines. Amines, if they take H plus and converts into a conjugate acid, then you can see this is a Lewis acid and this is its conjugate base. And if conjugate base is more stable, that means conjugate acid is more stable, that means the base is more basic in nature. So you can see more availability of lone pair mean more basic, or stability of conjugate acid also means more basic in nature. So you can see here it is more plus psi effect, then this is slightly withdrawing, triple bond is more withdrawing. So this is how the basic character varies. You can see two double bonds are more withdrawing, one double bond, then no double bond. So this is how the basic character would be. Clear? And next you see ethylamine, and that is ethylamine, and then you have sp2 form, and then we have sp. This is called amine, this is imine, and this is cyanide. Got it? Or nitrile. So you can see in the case of amines here, nitrogen has, a lone pair which can donate more easily, correct? So this is sp3, then we have sp2, then we have sp. See, hybrid is if the percentage s character increases, basic character drastically decreases. Okay, next check out. This is benzanamine. Then we have ethanamine, double bond, and this one. Now here, the lone pair is giving resonance, because of which, if there is a lone pair involved in resonance here, its basic character will decrease. So B will be greater than A, then C, then D. Okay. Next, if we have A, B, C, D, E here, check it out. This is sp3. How do we check out? Basically, you check out hybridization first. This is sp3. This is sp3. This is sp2, and this is sp2, and this is sp. So usually sp3 should have the most basic character, so A is correct. Then this, between these two, this is an exception because of the more resonance nature of amines compared to that of pyridine. So you will see pyridine has more basic character than aniline. So A, C, B. D again, because of amides being highly resonance stabilized, it will be less basic in nature. And last comes nitriles or cyanide. Okay, so that will be A, C, B, D, E. Then A, C, B, D, E. Done. Check out. Next one. If you have pyrrole, I mean this one, cyclohexanamine, aniline, pyridine, and piperidine. Check out these cases. Here we have complete sp2 hybridized aromatic group. This is due to aromaticity. And this is completely sp3. Okay. And this is sp3 but with resonance here. And this is sp2 without resonance. This is completely sp3. Now remember, between cyclic and open chain, if your hybridization is same, the cyclic will always have better basic character. So therefore, piperidine E will have better basic character than B, then D, then aniline C, and last comes pyrrole. This is the order. Okay. Please check both the cases. See, there will be ortho effect even when it comes to anilines. In anilines, if the ortho effect, that means any SIR group is there, a bulky group is there, bulky group will always decrease the basic character. So ortho will become the least basic. Unlike in the case of acid, benzoic acid, there the acidic character is increasing. Here the basic character will decrease. That's why you see conjugate acid of anilinium form decreases in stability. All SIR groups can show ortho effect. Okay, all SIR groups can show ortho effect. SIP is observed due to SIR groups at ortho effect. SIP means nothing but steric inhibition of protonation. So it is very less likely that amine will take H plus because it has to handle a lot of repulsions, right? So this phenomena of not accepting H plus is called SIP, steric inhibition of protonation. Okay. So if you have NO2 at ortho position, that will be the least basic. You can see this is the least basic. And at hydrogen, there is no withdrawing, only hydrogen. At meta, it is withdrawing by minus I. Para, it is withdrawing by minus I as well as minus I. Okay. So this will be the order. If you have methyl here, again same. Para will be most donating, then meta, then hydrogen, although it will be the least basic group. Same COR, we have hydrogen, because at other cases they COR will act like withdrawing group. Meta, it is less withdrawing. Para, it is slightly more withdrawing, although it is ortho effect. Ortho effect is not followed very well in the case of these two, OH and OCH3. So you better check out this, actual form. In the actual form, ortho will slightly be greater than meta. Here also ortho will slightly be greater than meta. So only two cases you need to remember, which are exceptions. Okay. Next is guanidine cases. Guanidine means when you have a C double bond N and then another bond is connected with NH2, then the lone pair of nitrogen can easily bond with a double bond, and that can create resonance. So that means if this nitrogen which is localized, if it takes H plus, you will get this NH2 plus. And due to the lone pair, movement of this pi bond here, you will get uh, conjugate acid resonating structures, and all of them will look alike because they have equivalent resonating structure nature. Their basic conjugate acids are very, very stable. Now if this is very stable, that means this is highly basic in nature. So guanidine is highly basic in nature. Girls, clear? Right. Now you can see this is a guanidine form, this is half guanidine form, this is only imine form, this is amine form. So answer should be A, B, D, C. Okay. Next, if you have basicity to be discussed in aqueous solution, check out ammonia. When you react with water, it will become NH4 plus and OH minus. So now, if NH4 plus is becoming stable, that means ammonia is more basic. So the stability can be derived because of two factors. One, if it has any donating groups on it, or second, it itself is a positive charge. So a lot of water molecules can accumulate it. So that is called solvation. So if solvation is more, then the basic character is more. Okay. So you can see tertiary amine, when you react with water, it will become R3N. So here solvation is very less, but on the other hand, plus I is dominant. So from one end, solvation is dominant, from the other end plus I is dominant. So experimentally it has been found that the basic character will be somewhere in between like this. So 2 degree will be greater than 1 degree, will be greater than 3 degree, greater than amine, I mean ammonia. This will be the order for methyl. If it is ethyl, then 3 degree will come before 1 degree. Okay, overall order is this one. Clear? uh, Okay, I forgot to write one more thing which is given in NCRT here. Let me put that just before ammonia. Just before ammonia, it should be PHCH2NH2. Okay, benzyl amine. So benzyl amine is slightly more acidic than ammonia. Got it? Girls, clear beta? Now this is the order that you need to revise. Got it?